Hi guys, and welcome for the afternoon lab for the Wednesday. Today is March 24th. There is a question related to next week because of the holiday. Again, there is no classes. So what I'm going to do, I'm going to record the lab also for next week, and hopefully you guys will complete your lab, because when I counted the number of days left, I think we really need to catch up on materials. So I'm hoping that's not going to be a problem for you guys, especially since the instruction is online. And some professors, basically what they do, they record everything and they give it to their students, and they don't do live stuff. So, okay, so that's the approach, at least for next Wednesday, the way I'm going with it. Okay, so this is basically for next lab, but today's lab should be, first of all, I must remind you of the rubric and how things work and so on and so forth. Let me check if there is anything special about this lab. Oops, it took me completely out. I don't mean to go out. I just want to stay in the instructions in here. No, there is nothing special other than the fact that you have your own rubric and you have everything else. So let me go and share with you the screen for the instructions for the lab. Share. Okay, the lab is on Ohm's Law. Okay, again, there's the introduction in here. This is the stuff we saw last Monday, Ohm's Law, really, V equal to Ri. And the cross section for a wire, which is PR squared, and the details that you guys all know and love by now. We wrote it both format sigma E and 1 over rho E. Both of them are actually what is the correct basically formula for Ohm's law, and this led us to V equal to Ri, what we call Ohm's law. So this is what we're going to check, actually, not this one. We're not going to be measuring the current density in the electric field or anything like that. We're going to check this one. We will have a voltmeter to measure our voltages, and this is what we do in the lab, by the way. And we'll have an ammeter to measure our currents, and we actually have also an ohm meter to measure the resistance. And we verify this law. So basically, that's what we do in the lab, more or less. And then we connect them in several configurations. We take two resistors, and usually they are color-coded. Like I said in the beginning before, I don't know if we started recording when I said that or not. When I showed you guys that resistor, it has some specific colors. And those colors mean something. It tells you what is basically the power, what is the sig fix, the precision. It tells you actually the value of the resistor in there with the precision that is in it. Now, if you don't have that, and if you don't know the colors, in the old days, there is a chart that you go by, okay? There is an app, I'm looking for it on my phone. Let me see if I can find it. There are several apps, okay, so it's not just unique to this one. All you have to do is just go to your app store and look for a color-coded resistance or something like to decipher colors for resistors. So that should be there. Hold on, I don't find mine. Where is it? Did they remove it? Should be with this group of apps, and I don't see it in here. No, I don't see that. Anyway, I used to have it. Okay, maybe it's in here. Oh man. Anyway, look for an app that gives you the color coding. I guess I removed it because I'm not using it anymore. That's what happened to it. If you go to the app store of any phone, whether Windows or Windows, whether Apple or another phone, you should be able to see it. I have an iPhone in here, so let me look for it quickly, because it's a good app to have, especially if you're going to have develop a hobby for electronics. So it's a good thing to have. So to know what kind of resistors you have, because you would want to, because you have a bunch of them laying around in front of you, and you don't have all the time to really test each and every one of them. So probably you just pick up one and then test that one, and if it is, then use that one. So I'm looking for resistor code calculator. Okay. So I used to have this. Well, it says open. For some reason I have it, but I couldn't find it on my phone. So I don't need to get it. I use this one. Again, I don't. So this is the app I have in here, okay, on my phone. So, and it gives you the choice between the 3-band, like the one that I'm showing right now, or the 4-band. Okay, all you have to do is just select the other one. And then each band has a specific color, and each color has specific value. As a matter of fact, all you have to do is just punch the colors. Like if I have a brown and a green, for example, the green is for the precision, I'm sorry. Yeah, what is this color? Orange, and another red, for example. And I choose, for example, a 10 in here. So it's going to give me the value on the top, exactly how much this resistor is supposed to be. So I don't have to, with the precision also. So I don't have to do anything. Obviously, I have to test it if I'm going to do electronics and I have sensitive equipment in there. In other words, if I put too little resistance, I might short circuit something and it starts smelling fire, okay? So you don't want that really. So you really need to test still the value with your good multimeter device. So that is important in a sense that when you're dealing with electronics, you need to know the values. For capacitors, and I don't know if I showed that last time or not, usually capacitors have their values are dependent to it. I don't know if you can see this one or not. It's too close. No, can I change the camera in here maybe? Yeah. So right now, if you can see it, it's 200 or 22 microfarads. Yep, it's 22 microfarads, and it gives you the tolerance. This is 400 volt, basically, capacitor. So this is 22. This is also the same size, I think. This must be also 22. Yep, that is the same thing. Both of them have the same value in here. So this is basically what you, if you are into a hobby of electronics, that's what you need to know. This is an integrated circuit. I think I showed you the older Arduino already. Okay, and this is already mounted to it's the breadcrumb in here. Okay, so it's the same Arduino board in here. Okay, a bunch of them. Anyway, so if you are into electronic hobby, that is something that you need to have on your phone, is how to read the proper resistance for the to put it in with the circuit. If you take too big of a resistor and connect it in parallel with this diode, for example, you're not going to see any light coming on because there is not enough current to light this one. Okay, so if you take it too small, you might burn this one. So you need to have the correct value for it to really, if you're going to do circuits with this one, to really have something significant. That's why it's very important to carry with you the proper, basically, ways of finding out what kind of resistor you have. So let's share the screen still. In this lab, you don't have to deal with that, especially since we are online. I mean, we don't do that. If we are on campus, and you will be given a bunch of basically resistors, and you're supposed to use, for example, 100 ohm in a specific configuration, or you're supposed to use 470 ohm, or 1000 kilo ohm, 1000 ohm, or kilo ohm, or 10 kilo ohms, or something. You need to really be able to pick that one up, and usually they're color coded. There is no values in it, and like the capacitor, where you can see the value. So the only thing you go by is its colors. And you have to make sure that you pick up the right one. So what you do in this case, you pick up your phone and you start basically checking to make sure you have the correct resistor. It's very important you do that. Okay? Otherwise, you could run into trouble. So again, these are in series. So the R equivalent goes like the sum of the R's. The R equivalent, when they are in parallel, goes like when the sum of the inverses. This we have seen already. This is opposite to what happened in capacitors. So we have seen the theory in here on how to connect resistors. So if you connect, for example, 100 ohm and 470 ohms, you're going to end up with 570 ohms in this configuration. But in here, you're going to have 1 over 100 plus 1 over 470. And when you add the two numbers, the two inverses, you invert it, and it should be less than 100 ohms. When you put resistors in parallel, the equivalent resistance is less than the smallest of them all. When you put them in series, the equivalent resistance is bigger than the biggest of them all. So basically, that is how you can remember these things. Here is the deal. Objectives are very important, so please don't just throw in any language in there unless you really know what you're doing. So what I suggest you do is try to understand at least what we're doing, okay? Once you have that understanding, then come back to the objective and thoroughly make it concise, precise, right to the point, complete sentences, not bulleted items, one complete sentence, one complete paragraph, I'm sorry, one paragraph, okay? At least 2 sentences or more describing exactly what we need to be done in this lab, okay? So that is what I'm looking for in here. I really want you guys to be able to communicate your ideas clearly. I want you to really be proficient in your communications when you're talking about these things, okay? This objectives, again, this text in here are rich text formats which enable you to at least catch the mistakes, namely the typos, if you wish, but don't over rely on it, because some scientific terms are, for example, not in this dictionary, so they might be flagged as incorrect. But that's one thing. The other thing also, you have to really have your idea clearly communicated. Do not just throw in some nonsense stuff in here that does not make sense to anybody else who reads it. It may make sense to you, but try to think of the person who's reading your objective and make sense to him or her, okay? So the objective is a very important thing. And it's important also in a sense that it's connect to the entire lab, what you're doing in the lab. And then at the end, it needs to connect to the conclusion. Case in point, we know we're going to verify this law, okay, Ohm's law, okay? We know also, probably, depending on how it goes in the lab, we're going to check this one. When I take more than a resistor and put them in series, we probably are going to check this one too, when I take a bunch of resistors or 2 resistors or more and put them in parallel. So probably this is what needs to go there, okay? Without having to put formulas or anything like that, okay? So this is basically what needs to be communicated somehow in the objective. Here is the simulation that we're going to rely on. And here are the instructions. So this is how it's going to look like in here. You may or may not choose to show the electrons. Don't show the electrons, just go with the conventional, basically how the current is flowing. Since this is a positive of the battery, so the battery is going to go like this. The current is going to flow from positive to negative. And if you follow the instructions, it tells you the wire resistivity is small 1, the battery resistivity is small 1, and then you start working with that to make it more realistic, okay? To make it more realistic. You're going to grab a voltmeter from the bunch in here, and you're going to grab an ammeter from here, and you're going to grab a bunch of wires from here and a battery, and you're going to bring a resistor in here, at least 2 of them, because you can clearly see you have an R1 in here plays the role of a rheostat. So what in the world is a rheostat? Rheostat is a resistor that you can dial in its value. So you can change it basically from something to another thing. So you can change RE in here, but R1 is fixed, basically. It's like this color-coded stuff. Some other resistors, they have this dial actually that you move in and out, and in doing so, you're going to have more or less of the part of that resistor that is contributing. So in other words, its value is controlled. So RE in this case is supposed to change, okay? So here is the instructions. Basically, the resistivity should be there's a B in here missing, small but not tiny, okay? Make sure the internal resistance of the battery is between 0 and 1. In this case, it's 1 ohm. 0 and 2, in this case, it's 1 ohm. And click the resistor R1 and fix its value to 5 ohms. So this needs to start with 5 ohms. That is R1 is equal to 5 ohms. Click on the battery and fix its voltage to 120 volts. So this needs to be 120 volt power source, okay? In practice, this is too much of a voltage, by the way. If we're doing this in the lab, we do a 6 volt, we do 12 volt, but 120 volts is a lot of voltage in there, okay? So you start smelling things in there, unless this resistor is a very high resistance, but it is not clearly in here. So this is an idealization, if you wish. So you always think when you're doing this lab, so what happened if tomorrow they tell us, you know what, you can go back to campus? How are we going to do this lab? That is a good point to me. The only reason why these numbers are actually good is because the precision, the tolerance of these devices then becomes good, because you can put a lot, you can get far better precision this way, but it's not how it's going to work in the lab. As a matter of fact, that is something I made a big fuss over when we were doing the lab, when we were doing the lecture, is that this thing will heat up, okay? And once it heats up, its value depends on the temperature, so its value starts to change from 5 ohms to probably fraction above 5 ohms and so on and so forth. So the voltage in here starts to change. So if you read the voltage now and you expect it to be 5 ohms, it's not. So there is an error in there. So that's why you technically really need the switch in here, okay? And that switch is here actually. So just to make sure you control this, you open it when you're doing the reading and when you're writing stuff and doing things to cool down, and you close it just to make the reading. Once the reading is over, read the voltage and the current, that's it. Then you open it again. So this is actually how this is done in the lab. You don't really have this one. There is a switch, okay? Unless you're coming in and out very quickly, then that's fine. But if you're going to wait there for a few minutes, like 20 minutes or 30 minutes, this value will change. It does not change drastically after 10 minutes, but it starts to change after probably half an hour or so, because this will become so warm, become so hot, especially with this kind of configuration. Because look at the current, the voltage in here, 120 volts, and this is 5 ohm, and this is 12.5 ohms right now. That is too much current running through this one. And that is going to dissipate a lot of heat, okay? So let's assume that we're still in this basically virtual world where we have no control over these things, or at least no appreciation of these things, which are really practical things, okay? Click on the ammeter and drag it to the other side and measure R1. No, I'm sorry, before R1 to measure I1. So we need the current basically on I1, which is the same current for the entire circuit right now. We're going to do that. Vary the rheostat from to obtain 6 different values of the current. So basically vary this R in here slightly and change it and change it and change it until we get 6 values for both V and I. So we need that, okay? So we need to change that, because if we change it, the voltage will change. The current also will change. So at the end, we're going to plot V and against I. So we're going to plot that, and should be a line, and the slope should be 5 ohms. Now that's basically what this whole thing is about. Better to obtain, okay. Replace the R1 by another 10 ohms. So basically you can throw this one or just change the value to 10 ohms. If it was really a lab, when we're doing it really, you have to actually physically unplug that resistor, bring another resistor and put it in there, and make sure the reading on it is 10 ohms, okay? Once you do that, then you're ready for the next step. In here, just change the value, okay? Where is it? Here. As shown, alternative, you can change the value of R1 to be what is this? I don't remember what I was writing in here. Anyway, just change the value of R1, okay? Again, repeat the different values of the rheostat in here for 6 values. And now let's look at this table in here so that you understand what's going on. So we have the first value of R1, which was actually 5 ohms. We measured voltage and we measured amps, voltage, amps, 1, 2, 3, 4, 5, 6 times by changing that rheostat, okay? So when we do that, we'll have different readings for the voltage and the current. Now we change R2 from R1, which was 5 ohms, to 10 ohms. We're going to do the same thing again, okay? So we're done with this parts. What is it? Up to 3 in here, up to 4, actually, we're done with it. 5. Now take the 5 ohms and the 10 ohms and connect them in series and do the same thing. So now we're going to take this circuit in here. We'll actually have to have another resistor now, break it in here and there, and connect another one in here and start doing the measurements like before, okay? Except now the voltage reading need to be between them, between the first resistor and the last one, and that is going to have the voltage across both of them. And now we're going to measure the result of the voltage and the current, the voltage and the current. The slope now should be 15 because they're in series, okay? And we're going to have okay, the average in here for R, for the slopes, okay? Or actually the current is fine. the voltages. Now we're going to do the same thing in parallel. We're going to take these two resistors, a 5 and a 15, and put them in parallel and start doing the measurements again. So we'll have a V and we'll have an I, and we'll do the calculations again and report the data 6 times and here again in the table. So if we do that, calculate from the table the values of R1 and R2. That would be just the slopes, okay? They should just be the slopes. From this data, the slope should be just R1. Compare that to 5 ohms. This slope should be R2. That should be compared to the 10 ohms, okay? Of course, you're going to find the difference between 5 ohms and this one. This one probably could be 4.8, or maybe the slope will be 5.2 or 5.3, okay? That is how you find the error. Find the difference between the two divided by 5 and multiplied by 100, absolute value, that is going to be the error. Same thing in here. Okay, the slope could be 9.95 or something, or 10.02 or something like that. In which case you can just take the difference between that and 10, and from there you're going to have the times 100. That is going to, after you divide it by 10 times 100, you're going to find the error in there. Is this acceptable? Usually, as a rule of thumb, if it's more than 5%, it's not acceptable. If it's less than 5%, it's acceptable. And the other thing also you have to be very careful with is that the fact that we're taking practical devices in here. So the overall R is a little bit different. Not only that, but the current in here is impacted by the internal resistor in here and the internal resistor of the wires. So a lot of things in here are implicated in this calculation. So usually you have errors. On top of, in practice, usually you have a problem, like I was saying, with the joule heating, okay? So that could cause that, okay? Calculate both R equivalent for the series and parallel circuits. So in here, I have just 2 R's in series. I have a 5 and a 10, that should be 15. In here, it should be 1/5 plus 1/10 inverted. So 1/5 is what? 2/10. So 2/10 plus 2, that's 3/10. When you invert it, it should be 3 1/3. So R equivalent in here should be 3.33 ohms, and R equivalent in here should be about 15 ohms, okay? So this is the calculated values. Compare the slopes in here. This should be, the slope should be about 15, okay? When I plot I in the x-axis and V in the y-axis, the slope should be 15. The slope in here should be a little over 3.33 or little around 3.33, basically, okay? So that is basically what this question is asking. And these are the graphs. Plot V versus I. So the x-axis need to be I, and the y-axis need to be the z-axis. Now, if you choose not to do this one and use Excel, which is perfect, then use it, okay? But properly label the axis for me, okay? Because that's actually a better way of finding do I require in here Excel? No. Graph only, okay? So if you use Excel, that's fine. That's great. If you can't use Excel, that's fine too, okay? So now you're going to, so, excuse me. This is 2 graphs in one. So this is V, this is I. One graph is for R1 and one graph for R2, 2 graphs. And this is also 2 graphs in one, okay? For both series, so there will be an R for series and another one for parallel. So there will be 2 graphs in here, okay? Now, do they pass by the origin? Because according to this law, this for I equal to 0, V equal to 0. So they must pass by the origin. Now you're going to check these graphs. Do they really pass by the origin or not? Okay. Is there a y-intercept, in other words? When you do the best fit, you're going to find the value. Okay. Typically, it should have a y-intercept because of the fact that there is issues with the experiments, okay? Calculate the slope of the resistance from the slopes and experimentally record the values. Now, here is the deal. We have the slope in here. We have the slope in there. I'm sorry, I made some mistake in here for this entire lab. I'm sorry, I apologize for it. These calculations are not relying on the slopes. You don't need to do slopes yet. You just use the average values. The average over the average should be that R, okay? For these calculations in here. So it's just the averages, which is a quick way of finding these answers. The average over the average, the average over the average. Just average these quantities. If it's a linear thing, it's going to, if it's a perfect line, it's the same thing. The average is going to be the slope. So that is basically what this is going to be. So all of those previous calculations are relying on that table. Now here is where the slopes are going to be. You calculate the slope for the first one, calculate the slope for the second column, you calculate the slope for the third column, third two columns, because you have both V and I. And then the last two columns, you find the slope in here. And then from the experiment, the resistance R, okay? The experiment tells you what this resistance are, okay? R1, R2, R. And this is the errors again. This have been calculated using, these errors have been calculated previously using the averages. Now it's the same calculations, but using the slopes. Now, what is the difference between ohmic resistor and non-ohmic resistor? An ohmic resistor is V equal to Ri. It's a line. Anything else is a non-ohmic resistor. Hopefully this clarifies this question. This is in general. It has nothing to do with this lab. So an ohmic resistor is a resistor where Ohm's law works. V equal to Ri. A non-ohmic resistor is like, for example, the diode, which is actually an exponential. It's not a ohmic, okay? Transistor also is non-ohmic. So this is a question in general. Now, analyze the tables. If the error justify non-ohmic resistance for this, analyze and determine. So basically, look at your data and your errors. Do all of your resistors behave ohmically? In other words, does all of these things looks like it's a linear dependency or not? Okay, if there is a discrepancy, please talk about that. Okay, finally the conclusion. Let's see the simulation now. Any questions about the entire lab, basically, before I go into the simulation? No? So let me share with you the simulation. Okay, so I'm going to bring let me first of all switch to this mode, okay? I don't like that mode, okay? So we need this one. We actually don't need we want the conventional, okay? So we want a wire in here, and let's make it a little longer, and make another wire in here, and turn it around. We need a resistor in here, a rheostat. We're going to have a resistor in here, and we're going to bring a wire just to make it neat and clean. And then we're going to bring another resistor. This is the one that we need to fix, okay? We need to click on the advanced mode to make sure this one is tiny, but not too big. This one sits at 1 ohm, okay? No, not real bulbs, okay. And we need a switch of some sort. Okay, we need another wire now. Control Z. Okay, we don't do Control Z, so let's cut it in here. Let me remove this for right now. Let me move this one in here because I need something in here. I need the an ammeter actually in here. Let's grab an ammeter in here, okay? Now we can drag this and move it nicely, okay? So let's fix the values first. First of all, we need the voltmeter. So the voltmeter will read in here because this is a positive side. So I'm going to put it positive and I'm going to put it 0. Right now there is 0 volt because there is no current flowing through the circuit. So let's double click on this value and put it at 5 ohms. So either I put it manually or I think I can control it. So if we're near, just click once. Can I change this one? I can't. So I have to put it 5 ohms exactly, okay? Now this resistor, we're going to put it somewhere in here, okay? No, not too big. I think we had a 12.5, okay? So this is 12, that's good enough, okay? So now, where does it show the values? I need the values, okay? This voltage now needs to be 120, which is the maximum in here. Okay, so at this point we're ready. All I have to do is close the circuit, and it's closed. Now the reading on my voltage is 32.41 volts. The current is 6.48 amps. Okay, let's change this value in here to another value. This is 22 ohms. Now the voltage has dropped, the current has dropped too. I'm going to change this one more time. 36. This is, of course, I need 6 values, so it doesn't matter which one I need. At least I have so far 3 values in here, okay? And continue with this one until I exhaust all of my things here. So let's, can we open the circuit? Oh, yeah, we can. Okay, technically that's what we should really do. We're gonna double this value in here to 10. 10 actually. Can we bring it closer in here? Man, cannot control it. So I trust that you guys are careful enough to get your values in here correct. So 10 ohms. Again, I'm going to start with a new value in here and here, somewhere low. Okay. Close the switch. All you have to do is click it once and it's going to click and open. So right now the voltage is 53.30. This stays the same. The amp is this much. So now if I change this value now to another one, voltage change and so on and so forth. Okay. Let's close this, open the circuit. Let me cut this point in here. Let me cut this one in from here also. Let me move the ends of the voltmeter and take this resistor and put it in here. Okay. Take another resistor now and bring it into the question in here. Make sure that this resistor, if I click on it, bring it to 5. Okay. Take another wire if you really care. Put it this way, another wire in here, and another wire in here. And this wire probably connects, doesn't matter, I don't need it, okay? Now it's in here. This is actually the same thing. I have them in series because the voltage across both of them should be the same. It's this voltage in here, okay? And let me start. I did them in parallel. I'm sorry, I didn't know that I was supposed to do the parallel first. It's fine, because this is my starting point. I'm gonna close the circuit. The voltage reading right now is 25.71. So this is the last column. The current is 7.581. And I'm assuming that I can do this 6 times by just changing the value of this resistor. So each time I'm going to change the value of this resistor, the current changes and so on and so forth, okay? So we're going to need 6 values for this one. So let me open the circuit one more time. Move this out of the way. Cut this connection, cut this connection, cut this one, and this one. So let me click on this, and can I delete this? And remove this. Oops. I guess I can't. I'm just moving them out of the way, okay? There is another way for it to just restart in here, refresh. I think if you double click on it, can I? No? Ah, here it is, delete. Good, I forgot about that. Okay. Click on the actual item, the delete button becomes available. Good. Then I probably could have done for the others. Okay, so let's move this one out of the way. So we're going to connect this one, and we're going to connect this one to it, and they are in series. It doesn't matter which one goes first, okay? So no, as long as I have them in series, you put them in here. Let's move this one to look symmetrical, more or less. Okay. So now we're going to do the same thing. Close the circuit. First of all, bring this down to our starting point. Okay, that's fine. And then close the circuit. And now this is how much voltage we have, and this is how much current we have. Change this value. This is in series now. And the voltage changes and the current changes. Does this lab make sense to you guys? Okay. So you guys are, I'm going to leave the session open if you choose to. If you want to finish this lab later on, that's fine. I think I expect this lab to be done very quickly, and you guys will have your data. Make sure you're careful with your data. And that's it. So everything should be fine. So if you choose to do it later on, that's fine. If you choose to wait with me in here, that's fine. So I'm going to stop the recording first.